In this video, we are continuing our quiz 3 review and talking about independence. So recall that events A and B are called independent if the probability of A intersected with B equals the probability of A times the probability of B. So this is the definition of two events being independent. And we've also seen that we can write this in equivalent way. So this is equivalent to saying that the probability of A given that B occurs is equal to the probability that A occurs. So in other words, whether or not B occurs doesn't affect the probability that A occurs. Or if I were to switch the roles of the A and the B, this I can also write as the probability of B given that A occurs should be equal to the probability of B straight up. Alrighty, so let's do an example. So in this example, it says for each of the following pairs of events, determine if they are independent or not. So the scenario in part A says, Naomi eats lunch on campus 85% of the time and off campus 15% of the time. Regardless of where she eats, there is a 40% chance that she will get a T. We pick a day at random. So the example says, let C be the event that she eats on campus and T be the event that she gets a T. All right, so I want to begin by giving you the opportunity to try this. So pause that video for 3 minutes to try this question. 4, 3, 2, 1. Pause the video for 3 minutes to try this. Alrighty, so hopefully you've done that. Hopefully you paused it and tried this for 3 minutes. Let's talk about it together. So we can handle this with a tree diagram. And one of the things that indicates that we may want to try a tree diagram is the fact that there's two stages to what's going on here. There's a matter of where she eats lunch, on campus versus off campus. And then the second stage is the matter of does she get T or not? Okay, so when we draw this tree diagram, one of the stages is her lunch spot. One of them is a matter of does she get T or not? From there we can form the outcome and list its probability. All right, so let's start where we begin with this tree diagram. Okay, so for the lunch spot, so she could either eat on campus, which is C, or not on campus, which we could call C complement. And then from each of those, either she gets a T, which is T, or does not, which is T complement. Same thing from C complement. She could either get a T or not get a T. So the outcomes are CT, CT complement, C complement T, and C complement T complement. So now let's fill out some of these probabilities. So it says that she eats lunch on campus 85% of the time. So this is 0.85. And off campus 15% of the time. So this is 0.15. And then next it says, well, regardless of where she eats, there is a 40% chance that she will get a T. So regardless of whether we're at C or C complement, the branch going to T in each of those should have 0.4 as the probability. So that means that the missing probability on each of those going to T complement is going to be 0.6, so that these two numbers add up to 1. Same thing here, it should be 0.6, so that these two numbers add up to 1. And now we're ready to write down our probabilities. So this is 0.85 times 0.4. This will be 0.85 times 0.6. And then we'll get 0.15 times 0.4 and 0.15 times 0.6. Okay, so we can write down what these multiply to. So the first one is 0.34. Then is 0.51, 0.06. Let's write that 6 better, 0.06, and then finally 0.09. Okay, so we're ready to test for independence now. So let's check if the probability of C intersected with T, these two events, is equal to the probability of C times the probability of T. So I'll put a question mark above the equal sign because I don't know if they're the same just yet. Okay, so for C intersected with T, well, I see that outcome here. So its probability is 0.34. So that side's not bad, 0.34. That's going to be equal to question mark here. Okay, and now what's the probability that C occurs? So C was whether she eats on campus or not. So that probability is earlier in the diagram. Here's probability of C. So I'll write 0.85 there. And I'll multiply that by what P of T is. This is the probability that she gets a T. Okay, so there are two outcomes that correspond to her getting a T. There's this one with this probability. There's also this outcome with this probability. So I'm going to add up those values. So 0.34 plus 0.06. Okay, so those are the values in pink there. And if I multiply this, I'll end up getting 0.34 on the right as well as 0.34 on the left. So these are equal. So I'll put a check mark here. Okay, so as a result, we can say that these events are independent. So there's two quick things I want to point out about this example. So let me zoom it out a little bit and then go to slightly earlier in the question. So one is, when I found the probability of T, which I got by looking at these outcomes where T occurred, if I were to add these values, we get 0.4. Notice that that is 40%. And the question actually told me there's a 40% chance that she will get a T. On a conceptual level, that makes sense, that the probability of her getting a T would be 0.4 because the question told me, well, regardless of where she is going, there's a 40% chance. Conceptually, this is my other note about this. One of the ways I could tell before even doing the test that these events are going to be independent is independence on a conceptual level is whether one event occurring affects the odds of another event occurring. And in this problem it says regardless of where she eats, so whether she eats on campus or not on campus, there is still going to be a 40% chance that she will get a T. In other words, where she's eating is not affecting the odds of her getting a T or not, so I would expect them to be independent. So it's good that we got that they were independent while working this example out. All right, let's do one more part of this example. All right, part B says, in a bag there are 7 blue M&Ms and 3 red M&Ms. We pick one M&M at random. Let B be the event that we pick a blue M&M, and let R be the event that we pick a red M&M. So we're going to test B and R to see if they are independent or not. So begin by pausing the video, this time for maybe 2 minutes. This one should be a little bit quicker. And test whether these are independent or not. 4, 3, 2, 1. Pause the video and try this one. All right, so hopefully you did that. Hopefully you paused it and tried this one for 2 minutes. Let's talk about this together. So this time we are going to check if the probability of B intersected with R equals question mark the probability of B times the probability of R occurring. Okay, so let's think about both sides. So B and R means that we need to pick a blue M&M and, because intersection means and a red M&M. But we are only picking one M&M. So if we're just picking one, we can't pick a blue one and a red one. That means this is impossible. And if that's impossible, that means this probability on the left-hand side is 0. Okay, so that made the left-hand side pretty quick and simple. Okay, so now let's compare this to the right-hand side. So the right-hand side, we got probability of B, the probability of picking a blue M&M. So there's seven ways I can pick a blue one out of, there are 10 total M&Ms here, because 7 plus 3 is 10. So 7 over 10 is the probability of picking a blue. In the same way, the probability of picking a red would be 3 over 10, because there's 3 reds and 10 total. Okay, so on the right-hand side, I'm multiplying 7 over 10 times 3 over 10, which is going to give me 21 over 100. And I can see that that is definitely not equal to 0. So because the two sides are not equal here, we can conclude that thus B and R, these two events are not independent. And that is our answer. And if we think about this problem on a conceptual level, if I were to do one of these events, like event B, if I were to pick a blue M&M, that definitely affects the odds of then doing event R, which is picking a red, because if we had picked a blue M&M, that definitely means that we did not pick a red one, and vice versa. So these events definitely affect one another. Sometimes in these probability and independence questions, it's not going to be clear whether the two events are related. And in situations like that, we really need to rely on this test to determine whether they're independent or not.